We'll continue our exploration of complex numbers. We're going to do them in polar form now. So if we have our complex plane, and this represents our complex number that has an A distance in the real plane, or in the real line, and a B distance around the imaginary. We can also represent this as the A component is our cosine theta, and the B component is our sine theta. But if we put this together, there's a unique theorem, de Mornay's theorem, which says that e to the I theta equals cosine theta plus I sine theta. And if we multiply this by r, we get r cosine theta plus r I sine theta. Notice the r sine theta is b times I, and the r cosine theta is a. So this form, r e to the I theta, will be the polar form. Euler worked hard to show that this relationship works, and we'll see that multiplications and derivatives work nicely with this. In fact, an example, just using the e to the I theta equals cosine theta plus I sine theta. Well, the derivative with respect to theta of this is the same as the derivative of this. And if I take the derivative of an exponential, I'll get I e to the I theta. If I take the derivative of cosine, I'll get negative sine theta. And if I take the derivative of sine, I'll get plus I cosine theta. And what I can do here is I can factor out an I. So if I divide this by I, pull out an I get 1 over I, negative 1 over I, sine theta plus cosine theta. And 1 over I is the same as I over I squared which is negative I. So if I rewrite this as I, negative times negative I sine theta plus cosine theta, or I cosine theta plus I sine theta. And this we knew was e to the I theta. So the derivative works. And so this representation, because it's easier to multiply and to do derivatives than calculus with, is a nice way of using complex numbers. That saves some mathematical operations for us. So how this helps us is we can get some rules from this. So first off, if we look at the magnitude of this, then it's cosine squared theta plus sine squared theta which is equal to 1. Right? Pythagorean identity, we get 1. So if we take the magnitude of anything in polar form with its radius times e to the I theta, then that's going to give us the absolute value of r times cosine squared theta plus sine squared theta, or we get r back. So and that makes sense if we look at the vectors that we created before. If I come back up here, the magnitude or the length, well, we've defined that to be r. So it comes back out within our relationships here. So this polar form becomes a nice way of working with this. So we can say that r is the magnitude of the standard form if we want to transform from standard form to polar form. It's noting that theta is not unique. Right? Theta is periodic from 0 to 2 pi. And so this repeats. Theta can be some base angle plus 2 pi times k, where k is any integer. And so these things can rotate around theta. So complex numbers can have more than one polar form. So for example, if I want to look at I in polar form, I has a magnitude of 1, and if I look at my polar form, that's going to be here, or when theta equals pi over 2. And so I can write this as e pi over 2. But that's the same as e to the I 5 pi over 2 as I add 2 pi to it. So there's an infinite amount of places where I can come in polar form. And this actually really helps us. In general, what we'll say is I is equal to the I times pi I pi over 2 plus 2 pi k. So I can actually convert a polar to polar form. So if I have z equals 1 plus I, if I draw this, I'm going to be 1 in my real form and 1 in my imaginary part. I come here, and so that angle is pi over 4. The magnitude of this, well, that's 1 squared plus 1 squared square root, or root 2. So I could write z as root 2 e to the I pi over 4 plus a factor of 2 pi. Some helpful things come out of this. E to the I pi theta whoops, not pi, sorry. E to the I n theta, some n multiple of the angle, is the same as cosine theta plus I sine theta to the nth power. Well, if we look at this n theta, that's going to be equivalent to cosine n theta plus I sine n theta. So taking powers on complex numbers in polar form goes much more quickly than it would taking the powers of the binomial. Also, if I am adding two angles, I get a multiplication in polar form using our exponential laws. Where this really plays out is if I have some variable to the nth power equals d. If we solve for d in polar form, so we'll say d is equal to its magnitude times e to the I, its root angle, plus 2 pi k. And we're going to say that this root is the principal angle. It's the one we solve for in the unit circle. And that means that it's wedged within the periodic domain. And A will be the magnitude of D. So if we rewrite all this in polar form with Z equals R e to the I theta, then and I can do Z to the nth, so I'm going to put these together and I'm going to get R to the nth equals e to the I n theta, which means that this is going to equal to some whatever d was, a e to the I, the principal angle, plus 2 pi k. So I've taken the variable I've wanted to and I've put it in polar forms. And I've taken the number that it was equal to and I also put it into polar form. If we take the absolute value of both sides, we get this. And if we solve this, then we get R is the nth root of A. So we know the magnitude right away. And if we look at the angles then, solving for n theta, well, that's going to be equal to theta naught plus 2 pi k. Right? Because we know this is equivalent to this, and this is equivalent to this. We can do these piece by piece in this format. And so we can say that theta is the principal angle divided by n, and then 2 pi k over n. And what we want to do is notice that these start repeating themselves as it moves through. So we can get one distinct value after k repetitions. So, right, if I look at this here, this comes back to 2 pi when this is k over k. So when n equals k, I get a repetition. And so if we start with n equals 0 and work our way up to k minus 1, we get k solutions. And this is a really nice way of finding some complex roots rather quickly. I'll start with one that, x to the fourth equals 1. This we can do using algebra, because that means x squared equals plus or minus 1, taking the square roots of both sides. And now I get x, well, if I take the square root of 1, I get plus or minus 1. And if I take the square root of negative 1, I get plus or minus I. And so there I have the 4 solutions that the fundamental theorem of algebra says that I should get for a 4th degree polynomial. And here the 4 solutions come out. If I look at these on my polar graph, there's 1, there's I, there's negative 1, there's negative I. And so theta should be the collection of 0, pi over 2, pi, and 3 pi over 2. Well, let's do this in using the polar description of these. And so if we use the polar description of these, the magnitude, so I'm going to have r e to the 4 theta equals, well, the magnitude of 1 is 1 times e to the I theta naught plus 2 pi k. So r is the square root of 1, or 1. And then in theta is equal to theta naught over n plus 2 pi k over n. Well, 1 has a theta naught of 0 because it's here. So that means I'm going to have start 0 plus 2 pi k over n. And we know we need to start with 0. So the first one is 0 plus 0, which is 0. The second one will be 2 pi times 1 over 4, which is pi over 2. The next one will be 0 plus 2 pi 2 over 4, or pi. And the last one will be 0 plus 2 pi 3 over 4, or 3 pi over 2. If I were to go one more and n is k, well, I get 2 pi, but 2 pi is a repetition of this one. And so this ability to solve roots with complex numbers leads us to a way of getting the repeated roots rather quickly. For this example, right, finding the square root of 1 works nicely, or the 4th root of 1 works nicely. It's a little bit harder if we're looking for the cube root of 1. Taking all polar forms into play. And so if we do that, r, again, if we put this into polar form, then my right-hand side is r I to the 3 theta equals, and 1 is 1 e to the I theta naught plus 2 pi k, where theta naught is still 0. R is still 1, square root of 1 equals 1. And theta naught will be theta naught over n plus 2 pi k over n, which equals, again, still 0, plus 0, so we get 0, right? We'll start with k equals 0, so we get 0 plus 0. But now we have to do 1, so we get 2 pi over 3. And then we have to do 2 or 4 pi over 3. And what this shows us is x cubed equals 1 has a solution on the unit circle of 1, but it also has a solution of 2 pi over 3 and 4 pi over 3. And if we think about this in these terms, 2 pi over 3 gives me a negative cosine value. Right? Negative cosine. If you grab your unit circle really quick, I'm actually flipping my unit circle open. 2 pi over 3 for cosine. Where's my unit circle here? I should hit pause, but I want to show how this unit circle works nicely for us. So let's see. 2 pi over 3. Don't have my glasses in. For a cosine value is negative 1/2. And then in for sine, it's root 3 over 2 I. And if we look at 4 pi over 3, it's negative 1/2 minus root 3 over 2i. And so there are these two imaginary roots to this that are lost. Satisfies the fundamental theorem. We have values that have meaning and are useful for us. And so this is the two forms of working with complex numbers. All right, that is the lecture on number sets. We'll continue with looking at what we can do with these number sets. We're going to look at the fields that come out of them and how we can create a general field theory, so when we invent things that are not numbers, because this course is going to be dealing with vectors and matrices which are not numbers, these patterns that we have invented to use for numbers, we can use for these new mathematical objects.